Hello everyone. In this video, we are going to look at the system identification application in MATLAB. So if you go to MATLAB and go under apps, then you can see here there is this app called system identification, which should be under the apps for controls. So if you go to control system design, then you can definitely see the system identification here. Okay, and if you click on it, you're gonna get this GUI, and then with this GUI you can import the data for a system, the input and output data of a system that you don't know the model of it at all, or just to some extent. And then this app will help you identify the model and or the parameters that are unknown in the system, which we call system identification. When you want to do control on any system, first you have to have the model of the system, okay? At least the controls that we know, the basic controls that we learn, the classic control, state space control, digital control. When you want to analyze the stability, design a compensator, a controller like a PID, any other thing, you have to have an idea. Now, PID is a little bit exception, but in general, you have to have an idea of the model of the system. And when you don't have it, that is going to make the controller design a hard job. So that's why we many times do system identification. So system identification itself is a course. At least you need to pass lots of different topics first to qualify to learn about system identification. And then when you start studying it, you see that you need like one full course to understand it. So my goal here is not to tell you all about system ID, is just to show you how this application works in MATLAB. But there are a few things that I need to clarify for you before I jump into the app and show you the application. One of them is a black box versus gray box model. What is that? So a black box means I have a system with some unknown function. I don't know the structure of it. I don't know the parameters of it, nothing. I know I have given it some inputs. It gave me some outputs, and all I have is the pair of input and output. Okay, so I have no prior knowledge about it, about the structure of it. I don't even know what exactly the transfer function of the system, if it's linear or it's nonlinear, what it means, okay? And it's hard to interpret that. But when I want to create a model of the system, I need definitely a lot more data because I don't know anything about it. But the good thing is it's flexible because I don't know the structure of it and the parameters. So it gives me more degrees of freedom to pick. Now, there are different models that you can use to model a black box like this, like ARX, ARMAX, neural networks, data-driven models, and so on. On the other hand, if you know the structure of it, but you don't know some parameters, so for instance, you know it's a polynomial, right? In the numerator, a polynomial in the denominator. So for instance, it is a times s plus b over c times s squared plus ds plus e, right? It's a general second order system where these parameters a to e are unknown, okay? But the structure is known. It's a second order linear system with 1, 0, and 2 poles. You just don't know the parameters, right? Then you might call it the gray box. So the structure is unknown, the parameters, some or all of them are unknown. And these parameters have physical meanings, of course, and I can easily interpret that. Now I'm not super flexible, right? Because the structure is predetermined. And if I want to determine these parameters, I don't need as much data as I needed for the other one, but needs initial setup to make sure that the form between input and output follows the second order system. So in general, that is a major distinguishing between black box and gray box models. Okay, that's one thing. Now, when you go to this application here, the first thing you need to do is to import your data. and your data, U and Y, that you give to the system could be in time domain, could be in frequency domain. You can merge them together and can create an object. You can insert examples and so on. The thing is, for some of the systems, the frequency domain works properly well, but not for all of them. Time domain literally works for most of the models. Okay, so time model is the one that fits all of different models that I'll show you. Okay, all of these, but a frequency domain has limitations to which one of them you can apply. Okay, so if you want to, for instance, apply to nonlinear ARX models, it has to be a time data. It cannot be frequency data. And I show you how to put those data, time or frequency, U and Y together and create what we call a system identification object, which is putting those under one single object, and then as fills of it. Okay, and then the other thing we can do is when we bring the data, we can do some pre-processing on the data. Not always the data I have, U and Y, are directly ready to be given to a system and find the parameters of it. Sometimes I need to pre-process the data. Like what? For instance, there are only some channels of U and Y, right? If they are multi-channel input-outputs, right? Like consider like an image or something, then you only need to work on one channel of it. Then you definitely need to select the channel. If there are experiments in the data, then you might only pick those. If there is only a range of data that you want, okay, so you don't want all of U and all of V, you only want a portion of U and V, which are between so many indices or between so many values from A to B, right? If you want to take the means off from them, right? If you want to remove trends, if you want to filter them, they are noisy signals, right? If this number of data points is not enough, you want to resample it, or it has too many samples, you want to reduce the samples, you can resample. You can transform the data, like for instance, take it from time domain to frequency domain and so on. So there are all sorts of pre-processing that it also allows you to do, okay, which is really great. And once you have this data pre-processed, now you pick the system model. So what is it that you want? Do you want to estimate a transfer function? Do you want to estimate the state space model, right? Is it a process model, which we'll see? It has some predefined, basically, systems, process models that you can pick from them. Is there a polynomial? Is there a nonlinear ARX? Is there a Hammerstein-Wiener model, spectral model, correlation model, and so on? So you pick what kind of model you want to have, and then once you have the data, this one performs an optimization or a neural network and creates for you your parameters, and you can export it. You can see the model output versus the actual input-output data. You can see the residuals. You can see all sorts of different responses and see whether the model that you fit to the data matches your expectations or not. Okay. You can export them to the workspace. You can do it in LTI viewer, right? Linear time invariant systems. You can remove them, and there are all those models fit are going to populate in these windows. All the data will show here on this window. So this is a really comprehensive, very powerful GUI that you can work with. So there are some stuff that I need to explain for you. Those models that you have seen, right? Transfer function and state space you know well. If you don't, please refer to my videos under playlist controls, and I explain transfer function and I state space models. So there is nothing new in these, right? So a transfer function basically has a numerator and a denominator. You have to give it the order of numerator and denominator, and then it finds all of the coefficients for these polynomials. If it's a state space model where, for instance, your state vector x dot equals a times x plus b times u, and the output y is equals c times x plus d times u, then you need to find all of the parameters within matrices A, B, C, and D. Okay, so that is the unknown state space model and so on. Now, the process model let me show you. If you go to process model, these are well-defined systems, but first, of course, you have to give it some data. So first, here I show you that I made this code here that creates the data for different types of models. And when you run this code, it creates data for different types of models and also saves them all as data, as objects. It saves them as objects and also saves them in math files. In one math file, it saves all of this data. So when you load this math file here, right, which is called System Identification Data Complete.mat, it has all of these objects in it. Each one of them is an object that has the input and the output of that specific model. For instance, if you are dealing with a transfer function, this is how it's done. This is my system that I'm supposed to find these coefficients. So let's say I don't know them. I'm not going to give them to this GUI. This is my numerator polynomial, 0.1s plus 0.2, and denominator is s squared minus 1.5s plus 0.7. And then I created a transfer function with tf command, and then I pass to it an input u. What is u in this case? U is a combination of two basically sine functions with different, or sorry, one sine function, right? And this sine function basically has a frequency of 2.02 pi, right? Omega of that is equal to that. Or you can say the frequency is 0.01, and it has some extra noise in it, okay? And I pass this u to the system, and with the time, and the time here goes from 0 to n minus 1, which is to 999, and my sample time here is 1 second basically. So it goes and generates the output, and then I take this input and output and I put them in an object here, which is called data for transfer function. The way I merge that input and output into an object is using this command, id data. So it converts those pair into an object called id data and call it data.tf. Now, if you go look at data.tf in the workspace, you can clearly see that. Look here. You can see that the data.tf, look, you see it's an object, right? And if you want, look here. You see? Right? It's time domain data set with 1,000 samples where it has output y1 and input u1. The units are not specified, but we can specify them. It's not important. And you can look at data properties and everything here. Okay, and I can import it into the GUI, right? So that's one command you can do. And if the data is in the frequency domain, there is this other command, idfrd, that you can put your input frequency, so u of omega, and output frequency y of omega. You can merge them and put them in this format with the object with idfrd. Okay, now the important thing is the output has to be a complex number. So if you want to pass it to a system, you make sure that the data that you are passing is in the complex format. Look here. So for instance, here, look, you see here I have basically the response in the form of something j omega. You see, so they are not magnitude and phase. It is the g of j omega for a linear system that you have to pass, right? So for instance, if in this case with this transfer function that I had, if I wanted to create the data, then I had to create omega. For instance, omega equals log space of from 10 to the 0 to 10 to the 3 with, let's say, 500 data points, and then g, right, equals, or y equals what? Y equals basically the g of j omega, which in this case is basically 0.1 times j omega, right? And then plus 0.2. So that is the numerator. Dot divided by, because it's pixel by or value by value division, this is going to be j omega squared. So it is going to be -1 times omega squared, right? Or j omega squared. If you want, you don't like it, you can write it like this. So you can say j squared omega squared, or j times omega, basically the whole thing squared, and then minus 1.5 times j times omega, and then plus 0.7. Okay, and you form y like that, and then the data that you want to send in for transfer function frequency data, it is gonna be basically IDFRD of omega and y in this case. So you can do something like that as well, and then it is going to create the data in the frequency domain, and you can also import that as well in your system, in the GUI. So here I added those as comments for you. So if you want to, because I give you this file, if you want to generate the data, you know how to do it. So if you run this, you're going to get all this data populated in the workspace, and these are the data that you have. So there is a U, there is the input, which is the harmonic input with some noise, and now the noise is a little bit too much, but we can reduce it. We also have a Gaussian white noise E, which we'll talk about it later. This is the output of the status space model, the unknown model. This is the output of the transfer function unknown model. These are the outputs of the AR, ARX, NARX or NARX, ARMAX, BJ, and Hammerstein or Box-Jenkins and Hammerstein-Wiener output. So the goal is to estimate these 8 models, right? These 8 unknown models, the goal is to estimate them, where the input to the system is either U or U and E together, okay? So that is all we have. Let me reduce this. I guess it's a little bit too much noise, so I'm gonna reduce that and run it one more time. Yeah, I guess the input is, I mean, like, it's fine, but to me that was too much noise. So this is what we have, okay? And you see the models are known here. Of course, I have ABCD matrix, I have the numerator, denominator, but the only thing I pass to this GUI is just the input and the output, U and Y, or EU and Y. That's all I pass. I do not pass any of these coefficients or anything, right? You see the coefficients of AR model or anything. I'm not going to pass any of those. I ask this guy to estimate them, and we'll see how good it does that. So before I do that, I need to clarify these different models that you have. We know transfer function and status space. Let's look at these other models that are available in this GUI. One of the models that are available in this GUI is called the OE model, or output error model. Here, what you have is the output is basically a polynomial applied to the input plus some noise. This E is the white noise that is basically modeling the disturbance of your system. The U itself has some measurement noise, but E acts like the disturbance, as I said. B and F are numerator and denominator polynomials, and Q here is the delay operator. It's not the basically the derivatives operator, like in transfer function, right? You see these polynomials are in terms of S, and S, you know, that corresponds to time derivative in the time domain. But here, Q is the delay operator. This is like Z minus 1. So these models that you have, these are only in discrete space. They are not continuous. Okay, can consider that when you're doing it, that these models are all discrete models. The state space and the transfer function are continuous, or they could even be discrete, but clearly this OE model is only discrete model. It's only in the discrete space, not continuous. So it's a delay operator. And as I said, this is E acts like the disturbance, a white noise. Okay, so no correlation between the, if you look at the power spectral, is kind of uniform. The goal is to find the unknown coefficients in B and F. Okay, these are polynomials in terms of Q or Z inverse, and the goal is to find them. Okay, now the thing is, it does not really model, has any dynamics for the disturbance. Now here it says noise, it's actually the disturbance. It does not have any numerator or denominator to apply to E. So the disturbance has no dynamics. Only the direction, the relation between input and output has a dynamic that you need to find. Here, this guy has no polynomial. Okay, so this is when you want to only model the system dynamics, not the disturbance dynamics. Okay, that is one model you have. Then we have the AR and ARX model. What are these? So AR stands for autoregressive, and X means exogenous input. Okay, so what are these? The autoregressive AR model is similar to ARX, except it doesn't have input. So if you look at this model here, the input, the output, and all delayed version of the outputs are related to the input and delayed version of the inputs plus what? Plus the disturbance, of course. So if you want to write it, you can write it like this, where again, all of these delays are going to be forming a polynomial. So this one is going to be basically Q, right? That is going to be Q. This is like Q squared. This is like Q to the N. Okay, this is like Q again. So Q is like a Z minus 1. And you write it like this. So the output and previous versions of it are related to previous versions of input and some disturbance. Now you might say, what difference does it have with respect to the previous one? Well, the difference is the previous one and this one are not exactly the same in terms of disturbance. How come? Well, if you cross multiply or divide this bottom one by AQ, what would you get? You get Y to be B over A of U, and then plus E over A. So you see here, there is some dynamics that is affecting your disturbance. Here, there is nothing. Okay, so here, the system dynamics, this denominator, will affect the disturbance to some extent. So it's a little bit more complicated. Now, if the system has no input and only noise, then all of these U's can go away. So if you get rid of all of these U's, so your equation is simply A times Y equals E. So there is no input, then we call that model AR model, autoregressive only. But if there is input U, then we call it autoregressive with exogenous input. So that X is that ARX that you see, it has input. Okay, so this is an ARX model or AR model, depending on whether there's U or not. And then there is nonlinear version of that. So the nonlinear version of AR is called NAR, and the nonlinear version of ARX is called NARX, NARX. So NAR and NARX are nonlinear autoregressive and nonlinear autoregressive with exogenous input. What's the difference? The difference is this. Now your output depends on the previous version of itself, the previous versions of the inputs, but instead of being just these constant coefficients that you had, look, the relation last time was determined by these constant coefficients that you didn't know. This time it is by this nonlinear function, which could be any function that you don't know. Okay? And this one is not applied to the inputs, this nonlinear function. Okay, it's just applied to the previous versions of the output and input, not the disturbance. So this model is called NARX, and if you get rid of these U's, then we call it NAR. So this is another model that you have. Then we have ARMAX model. What is ARMAX? ARMAX means not only it's autoregressive, not only there is exogenous input, but also there is a moving average. Okay, that's called ARMAX. What is this? Well, let's take a look. This time, you have the output and the previous versions of the output are related to the input and previous version of it, and the disturbance is also coming into play with its previous versions. Okay, so now the disturbance, previous versions of the disturbance also showing up into the equation. So your equation, if you want to form it as polynomial, is a times y equals b times u plus c times e. This c that is added is the new thing. Now you are considering dynamics, full dynamics for the disturbance. And in this case, this nk, which is basically how many times you go back in the input, is called the input delay. And this NC, which is how many times you go back in the disturbance, is called the number of moving average terms. So this is more complicated. You see, as we go down, typically the systems get more complicated in these models. And then, of course, you can have NARMAX and make it nonlinear. So in that case, then you have nonlinear functions. So your y of t could be a nonlinear function of all of the previous y's and all of the previous u's plus another nonlinear function for all of the previous e's. Okay, that could be a NARMAX model if you ever hear that. And you can see that, or we can have all of these to be falling under the same nonlinear function, so we can make this f and g to be equal to each other. That is like a kind of simpler version of it. The one that is really complicated like this, we call it the Box-Jenkins model or BJ model. The BJ model, if you look at it, the inputs, outputs, and the noise relation is given by two separate transfer functions, B over F and C over D. And you might say, well, what difference does it make with respect to the top one? It seems quite a bit similar to the ARMAX. No. Why? Because here, if you divide in the ARMAX, divide by A, you get y to be b over a times u plus c over a times e. Here, the denominators are the same. Here, the denominators are different. Okay, so they have different characteristic equations for the disturbance and for the input. So Box-Jenkins is very, very complicated. Okay, you have lots of coefficients in B, F, C, and D that you have to find. Okay, that's very complicated model. We also have this model called Hammerstein-Wiener models. Okay, what are these? So in this case, for the Hammerstein model, your output is going to be a combination of two nonlinear functions of the input plus noise or disturbance, and between these two nonlinear functions, g and f, g actually is a linear function, really. It's not nonlinear because you see it's g of q. It's a linear function. F is a nonlinear one. But this is a static function. But g is the dynamic function, the one that has the unknown coefficients. F is just one single function that you have to find. G has a bunch of coefficients in it that you have to find. So you see now this is a very complicated nonlinear model. Okay, like you see in neural networks and so on. And this nonlinear model, it can show, for instance, dead zones in the inputs, saturations, and so on. So if you want to model saturations, then you can use this. And that f could be a saturation function, right? So that f could be a function like this. And then we have Wiener model, where here, as you can see, it's kind of backwards. The nonlinear function is out, the linear function is in. So first the linear is applied to the input, and then a nonlinear is applied to that. So G is linear dynamics, H is the nonlinear static function. And this is very similar to neural networks if you look at it, right? That first you have a fully connected layer, linear layer, and then you pass it to a nonlinear function like the ReLU function or a sigmoid function or any other function. And then we have, of course, combination of these, that here you have two nonlinearities, H and F, and then G is the linear in between. Okay, so these are extremely complicated models. Now, there are two other things in this GUI that I need to show you. One of them is called the correlation model. The other one is called the spectral model. So let me briefly mention them because my goal is not to define all of these systems in details, but briefly just what they are. Correlation models are the ones that are non-parametric. So here you don't have these unknown coefficients A, B, C, D, and so on that you need to find. The model has no parameters. The model between input and output is just due to the statistical correlation between them. So input and output are statistically, correlated to each other. Okay, there is no model with parameters that you fit. In this case, what you need to form is the cross correlation between the input and the output, and the definition of cross correlation for a specific tau is the expected value of y of t u of t plus tau, correct? Based on the probabilities. And if you determine this cross correlation between input and output, that is basically the same as your impulse response of the system transfer function, if there is a transfer function. So here you approximate the impulse response of the system by this cross correlation function, which is plotted or calculated for different tau values, right? So you basically have tau, and then you have r of yu of tau. And you get a bunch of different numbers for basically different taus, right? You have different levels, different values calculated. So you get something like a histogram or bar like that. And this is how you estimate the system, okay? So these are good for impulse response estimations and initial analysis. And then in the frequency domain models, one type of model that you can fit is called the spectral model. Okay, so here you need to find the power spectral density of the output, phi yy of omega, find the cross correlation between y and u, spectral density of it, phi yu of omega, and once you divide the phi yu by phi uu, that is basically your frequency response function. And actually, what we need here is uu, not yy. Okay, so this should be uu. That's what we need. And that is what goes into the denominator, and this cross spectral is what goes to the numerator, and we can again have the frequency response, right, by dividing these two spectrals. And if you want to know what is phi of uu, again, I have to make a separate video on the spectral densities, but if you want to know what is this one, this is the expected value of u of omega times u complex conjugate of omega. Okay, and then similar things can be defined for y, phi uy and phi yy. So just replace them with, for instance, y bar or u bar. So for instance, if you want phi of yu of omega, this is the expected value of y of omega, and then u transpose conjugate, complex conjugate of omega. And you might say, what are these functions of omega? These are the Fourier transform. Okay, so for instance, u of omega, if it's the continuous time domain, or basically discrete domain, then you can use it. So in discrete domain, you can say this is equal to sigma n goes from negative infinity to infinity of u of n times e to the negative j omega n, right? And of course, n does not go for the signal typically from negative infinity to infinity. In this case, it goes only from basically 1 to infinity, right, for a discrete signal. But a similar thing can be defined for y. You can find these spectral functions, divide and approximate your transfer function. So this one needs a video of its own. If I want to talk about the spectral densities, and if I want to talk about this correlation model, non-parametric, I have to make separate videos. So to promise you that, here I put a star next to these so I can explain them to you in separate videos and completely clarify them. So if I want to summarize, I have all of these models in this toolbox, from AR to NAR to ARX, NARX, ARMAX, NARMAX, OE, BJ, Hammerstein, correlation, and a spectral. And each one of them has a separate application and pros and cons. For instance, if you want to look at autoregressive and nonlinear autoregressive models, so the autoregressive one that has no input, they are only good for time series modeling, no system dynamics. Or if they are linear time series or nonlinear time series without a specific input from outside, and it's just due to disturbance, then they could be good. Okay, they are very simple, right? But they are not for modeling the input. But if you bring ARX or nonlinear ARX, now you have some inputs dynamics. Okay, so you can now model input dynamics, but ARX does not have the disturbance dynamics. Okay, but it's faster than NARX, because NARX is a nonlinear system, so it can model more complicated systems, of course. But of course, you can overfit when you are modeling, and the training of that is a little bit harder. And then ARMAX and so on. Now you have to model the noise a little bit better than ARX, right? There was some dynamics for the disturbance actually. And then Box-Jenkins, that has separate transfer functions for the system and for the disturbance, right? Hammerstein is when you had all of these nonlinearities. So it's like a nonlinear version of Box-Jenkins. That is very complicated. Okay, and this is really hard. The more complicated the system is, the harder it is to basically identify it, right? And as I said, each one has its own application. So ARMAX, you can say it's used in linear systems with colored noise. Well, now, what is colored noise? What is white noise? Again, that's a separate thing. When we talk about power spectral densities, we can talk about that. And then linear systems with negligible sensor noise, systems with complex noise dynamics, then systems with static nonlinearity but dynamic coefficients defined, and then initial systems on parametric modeling, frequency domain, vibrations, and acoustics. A spectral could be good, right? Because in vibrations, many times we provide an input with some frequency to the system, measure the output, so we look at the vibrations, and we have the data in the frequency domain. And because of that, spectral models could be good for identifying systems that are showing vibrations and oscillations. Okay, now that we have seen these different models, it is time to look at the MATLAB demo. Okay, so let's look at the MATLAB code. So this MATLAB code will provide data for all of those different models. You can download and run this. I'll give you a download link under video description. And then you can go ahead under apps, as I said, click on system ID and try to see if you can ID these systems. So here I'm gonna run this first for you, okay? And here are the data. Here is the inputs that I provided, and this is that error E, so U and E, and these are the outputs for different models, the state, the space transfer function, and so on. Now, I also have this other input, which is a simple harmonic with some noise. I can use that one as well, or I can just get rid of this part of the noise. But one thing I want you to pay attention to is that not every input that you use, you can exactly find the good model or very accurate model of the system. The input to the system, we say it should be persistently exciting. It should excite all of the modes of the system, all of the dynamics of the system. And typically in a linear system, a simple guide is, if you have n parameters that are unknown, make sure you have n harmonics in your input. For instance, if I look at this transfer function, and this transfer function has 1, 0, and 2 poles, at least I need 3 harmonics in my input to be able to find all of them. So not every pair of input-outputs that you provide to that application will be able to find all of these parameters very accurately. If you want to give it an input that has lots of different harmonics and variations in it, one input that you can generate is called ID input. And this ID input is not really a function. This generates different types of inputs for you. So I say I want to generate an input for the system identification ID with n numbers in it, but the input type of function, I want it to be PRBS. So the input is PRBS. What is PRBS? PRBS stands for pseudo-random binary sequence, which when I ran it, you can see that it's basically a bunch of numbers right here. Let me zoom into a small part of it so we can see better. Let's see, for instance, this area here, right? So you see that the number is jumping from 0 to or -1 to 1, correct? So you see it's back and forth jumping between them, and it shows kind of like a random behavior, but it's not really random because these numbers are generated from specific algorithms. And if you know those algorithms and typically what we call the seed of those random generators, you can reproduce them. So if you don't know what pseudorandom is, I recommend there is a video on my channel about pseudorandom numbers. You can look at that under playlist MATLAB. Also under playlist controls for adaptive control, I explained what is persistently exciting. So that is this video here where I talked about how random numbers are generated, which are using pseudo-random algorithms, and then what is the seed for them and so on. And then, as I said, if you look for persistent excitation, which is a common idea that you need in adaptive control and in system identification, if you want to know what is a persistently exciting input, then you can watch this video as well, okay? So here, make sure that your input has sufficient variations over time and it's not a simple harmonic or something, okay? At least it has several harmonic components in it, several different frequencies. And this is that white noise error. And then these are, as I said, the outputs of different models. So here, with this data generated, I'm going to go ahead and basically take this the output data of the transfer function and the input data of it, u and yt. I converted them into an object with sample time of 1, okay? I converted them to the data object with this function ID data, and now that object can be inserted into the application, and it can be used directly with the application to estimate the system. And look at the numbers I have: 1.2, 1, 2, and 3 in the numerator and denominator. So as I said, we go here and we click on the System ID app. Then we go here and say my data is time domain, and then it's an object type. And then the data, I saved it. If you looked at it, it was called data underscore transfer function. So you provide the name and say import it. It does. There we go. That's my data. If you want, you can pre-process it, but here I just go with the data I have and I say I want to estimate the transfer function. And it brings it for me. And then I said, I want a continuous model. If you want, you can go with the discrete model. And I have 2 poles and 1 0. I don't say where they are, what's the coefficient. I just let it decide. As I said, you can model delay if you want. In this system, I don't have a delay. You can change the system estimation options. You can change your solver, different number of iterations, and so on and so forth. Add regularization to avoid overfitting. There are lots of things, but here I just, for simplicity, avoid all of that and just estimate. And here, this match and this number here will tell me how good the match is. Look here, in this case, the match is 100%. And my cost function, which is the sum of the square differences between the model output and the actual output, is 0, literally. So that's 100% perfect fit. It doesn't typically happen this good, but look here. And one reason is actually I gave it a lot of information, 2 poles and 1 zeros. But if you zoom into any region here, you see that the gray line, which is the actual data, and the model output, which is blue, they are perfectly overlapping. There is no gap between them. If there is a gap and that output is not 100% or very close, very high number, you're not going to get very close to the system model. Okay, so let me show you now with this perfect fit that I have, what kind of transfer function I can export to the workspace. So I get out of here and I go back to my main window, right? I can even close this. The model is extracted, called transfer function 1. I drop it to the workspace. So now it is added to the workspace. And now here we go to the workspace and say, give me transfer function 1. And it does. And look at here. Look what it found. 1 plus 0.3 over s squared plus 2 plus 3. And that is exactly these numbers. You see, because my input was great and my system was not very hard. It's just a simple transfer function with 1, 0, and 2 poles. And the input was this PRBS, which has lots of harmonics in it, lots of variations. So I could do a perfect job, right? Now, if I go ahead and change my input back to the simple harmonic. So here I only have one harmonic in the system. That's all I have, okay? Nothing else. And let me run it again. First run it, make sure your system does not go unstable or anything. You see that this is your response, is clearly stable. And now I'm gonna run this again. So you can clean the data or you can come back and do it again. So let me go ahead to the apps and bring this guy up again and repeat the same process. So here we go. Again, it was called data underscore transfer function. Import it, close, go here, estimate the transfer function model, and then I will go for, again, the same thing, continuous 2 and 1, estimate. Let's see what I get here. Now look, it's 99.33% match. So it's great match, okay? It did great, actually. It's not 100%, it's really great match. And if you zoom here, you have to zoom a lot before you can see any gap between these data. But here, you see now there is some small gap. Okay, so it's really great. The match is really great. And now I close this and I export my transfer function back to the workspace. And let's see what's the function. Here is the function this time. Compare it here. You see this number is 0.9 instead of 1. This number is 0.11 instead of 0.2. And this number is 1, which is good. This is 2.5. This is 1.9. So clearly you see these numbers are off. And these numbers are off too. Although this system with this transfer function could match the output of the original one with 99 point something %, but they are not exactly the same. Okay? And it can happen that systems have a little bit different shapes of transfer functions, but actually their dynamics are quite a bit similar for a specific input. Okay? So one thing you need to look is the zero and pole of this system versus this one, how much they are off. For instance, the zero of this system is at negative 0.2. For this one, you have to divide that 0.11 by 0.93, right? So you probably get, I don't know, 0.12, 0.13 negative. So it's close to that, but not exactly. And then you have to find the roots of this denominator and the roots of this. And again, they are both big complex numbers, but a little bit shifted. But for the same input, which is only this specific harmonic, they can generate relatively close results. Okay. Now, if you change this to a different input and different harmonic or different things, you might get different results. Okay. So my recommendation is, if you want to do a very good job, my recommendation is go with this one. This PRBS, this is really good. It has all sorts of variations in it. And so it can do a great job here. Now, for instance, you can do the state space model, or you can do other things, right? So all you need is now go back here, right? So now you cannot delete the data like that, but it's fine. Let me just rerun this, although I don't have to. So here, let's say, again, my data is time domain and it's data, but this time I bring in something else. This time I bring in data underscore the state space, SS. Okay, and I import it and I close it. So I brought that in. and I want to approximate the state space model. Then it asks you some questions if you can provide. So what is the model order, right? So you can either provide the model, or you can say, get me the best pick in this range. So I'm not sure exactly what order it is. You can pick the best one. So here, to make it more general, let's not give it order 2 because my system is order 2, correct? But GUI, it allows me the option to say I just go with a pick. And I'm not going to give it the wrong number. So I say, get me the best order that you think, anywhere between 1 to 10, okay? And look at what it is suggesting. It's order 2. It says order 2 is the order to go for this system. How did it find it? It did find it based on these singular values. What are these? This needs a video of its own. So I will make one of my upcoming videos under controls will be the determining the order of a system with the singular value, okay, with singular values. And these Hankel orders, how do we pick the best order of an unknown system? So this is, again, explaining that is beyond the scope of this video because that's not what I want to do. But here you see that it is suggesting order 2 for me. And then what kind of state space form do you want? A free form, companion form, observability, canonical, modal. What format do you want? So I leave it as free. Again, you can add delays. Again, you can change the estimation or the method and all sorts of things. So let's say go ahead and estimate the state space model, which are all of the numbers in matrices A, B, C, D. And you see, again, it could do 100% perfect job. Okay, yes. So all I need is to close this and close this one and go ahead and send this to my workspace. So all I need is to go to SS1, correct? That was, I assume, something I sent to the workspace. And this is the system. Let's look at these numbers, see if it did a good job or not. And if you look here, actually it gave me a different set of matrices A, B, C, D. But remember that the state space representation of a system is not unique, okay? So depending on which parameters you pick as your state variables, you can get completely different state space representations, but still they can have the same transfer function. Okay, so you see that none of these matrices A, B, C, Ds are exactly the same except for D, which is 0. And you can repeat that for the other things. So if you see 100% match and you don't see the exact same numbers for state space, don't be discouraged. It actually did find the system dynamics, but it's a different representation. And then you can go for other models. You can go for AR, ARX, NARX, and all of these other models like BJ and so on. And by the way, you see that when I created this data, I did create them using the command filter. Okay, so you see for BJ, for Box Jenkins, I have basically 4 different polynomials, which corresponds to those polynomials here in the model. Right? If you look, B, F, C, and D, right? So in this case, these are the things that I provided, and then I can go and model that system or any other thing. Now, one thing I wanted to show you, so you just pick whatever you want to pick from here. One thing that I wanted to show you was these process models. So this is very interesting. If you look at process models, here you can fit a specific type of system transfer function to your data, which is predefined. So for instance, you say, hey, I want my transfer function, as you can see, to have 1 pole. And I want it to have delays. So you see it has 1 pole at -1 over TP1, and it has a delay of negative TD with a gain of K. Okay? So this is the system. Fit the data to this system. But if you want it to be a second order, here we go. You see, if you don't want it to have delay, there we go. If you want it to have 0 in the numerator, activate this, and you see, now you can have a 0, right? If you want to add an integrator and make the system type 1, then do this, and then an integrator is added to the system. Okay, so you can do anything. And then when it comes to these parameters like K, TZ, TP, and so on, you can check them and say these guys are known. Okay, and if it's known, for instance, if I know the K value, guess what? You have to say, hey, K is 2 and I know it. Okay, then it's not going to optimize for K. It only looks for TP1, TP2, and TZ, right? Or you can give it some range for that parameter. If you don't know it perfectly, but you know some range that parameter could be within, then you can provide that, right? So this can limit the optimization search region for each one of them and make your basically solution go faster. Or if you have an initial guess, you can provide that. Instead of saying auto-selected, right, you can say, hey, I want to do user-defined. And now I can say, well, I think TP1, you better start from 0.5 first. Okay, and this will really help your system get faster results. So this is really good for specific systems of type 1, 2, 3 or order 1, 2, 3 that you can add delays or integrators to them and make them more complicated. So this is also very good if you have some general idea. But as I said, you can have all sorts of these other models. You can go under polynomial. And under polynomial, the structure could be ARX, it could be ARMAX, could be OE, output error, or it could be Box-Jenkins, right? So you say, hey, I want to go with Box-Jenkins, right? And here it is asking you to provide orders, right? So 2, 2, 2, 1, and all of these 2s are for B, F, C, and D. And so I guess this is the case for me. In this case, all I need is to provide the appropriate data. And then if there is any input delay, I can do that, give it a name and let it estimate. So here, what I need to bring in is to go into the time domain, change this, and then bring this data that was called data BJ, right? So I can do that and import it. There we go. And now I deactivate this guy, okay? By clicking on them, you can activate or deactivate them. So my data is going to be this right now. Okay, and then let's see with this data if I can estimate the polynomial, a BJJ, and let's see if it can estimate for me. Now it seems like the data it is using is the state space one. Still, it's the state space one. So you have to be careful about this data here, right? Let's see if I can delete this data because it doesn't look like I can. And I need to make sure that I'm passing it. You see the validation data is this. Let me see. So if I bring this here, there we go, and bring this here, there we go, okay, and get rid of that, get rid of this, excellent, and this, and let me do it again. So go ahead. Okay, and you see at best it could do 59%. Remember, your model is extremely complicated model. Okay, it's a very complicated model, and it does not mean that it can do a perfect job. Now, it's not really horrible. I mean, if you look at this data match here, right, it's not super bad, but of course, matching that kind of system with complicated model like that, it's not an easy task. So you might not never get 100% on this system. Okay, so please pay attention to that. Now, one thing you have to pay attention to are these orders. If you give it wrong information and wrong orders, of course, it's not going to do a great job. In the case of this system, the orders are not exactly 2, 2, 2, 2, 1. Okay, so NB, NC, ND, NF, and NK, B, C, D, F. So look here, it's B, right? C, D, F, and if there is any input delay that you have over here, right? So let's go back to this Box Jenkins. Okay, so you have to make sure those orders are given correctly, and if there is any input delay as well. But if you go back and look here, this one is order 2. This one is not exactly order 2 because the first term, which is the Q operator, starts with 1, so that is 1, order 1. This is order 2. This is order 1, and there is no extra delay. So really, the order of the system should be this: 2, 2, and then because remember it's B, C, and you see B and C are 2, 2. The rest of them are 1. So we have to do with something like this. So let me estimate with this set, see what I get, if I can get any better results. And you see now I got a little bit better results. Okay, compared to last time, I got better results. And of course, again, I can go ahead and export them to the this next one, I guess, is the one that was better, right? And then I can, of course, export them to the workspace, and I can look at this, or actually it was this guy, sorry. It was this one, BJ2020 exists, that's fine. So BJ22111 is the one you had, and then these are those polynomials, okay? And they will not be exactly like these, right? So look, 0.2 and 0.3, you don't have here 0.2 and 0.3 necessarily because of only 57% match. So you should not expect this to just do a magical job and find these models all perfectly. The simpler the model is, the higher chance that you can get it all perfect. The harder the model is, the smaller the chance that you can fit everything perfectly, because you have to have some good guesses, right? So you have to go back and change your ranges, guesses, and everything. So hopefully it can do a better job, okay? But in general, models like BJ or Hammerstein-Wiener, these are quite a bit harder model to get everything perfect. So hopefully you learned basically how to use this application, how to bring in the data, whether it's in time domain or frequency domain. The best way is to form an object and bring the object. You can pre-process it, as I said, you want, and then estimate different types of models that I showed you a few of them, export them to the workspace. And then once you have a model in the workspace, you can compare it. If you don't have the model, the actual model, then this is the best model that you have, so you can use it in place of the actual system. And you can design the control for kind of this model as opposed to the original one, which you don't have access to. So thank you so much for your attention. I'll see you in the next video.